Welcome to the complement of Lecture 2 on C-star algebras, titled Normal Operators and the Continuous Functional Calculus. In this lecture, we are going to see a fundamental application of our work on unital abelian C-star algebras. So let me start by reminding you of our main result on that topic. So let's fix an abelian unital C-star algebra. Its Galvan spectrum is a set of its characters, that is a set of all unital algebra homomorphism from the algebra to the complex numbers, endowed with a weak star topology. As such, it is a compact Hausdorff space. Now, if we pick A, an element of our C-star algebra, the Gelfand transform of A is a function that to any character omega of the C-star algebra associate the value omega of A. And it turns out that the Gelfand transform of A is in fact a continuous function over the Galvan spectrum of the algebra. Thus we have a map which goes from our abelian unital C-star algebra to the C-star algebra of complex valued continuous function on the Galvan spectrum of our C-star algebra, and that map turns out to be a star isomorphism. Now we are going to work for the rest of this lecture with an arbitrary C-star algebra not assumed a priori to be abelian. Inside such an algebra, I can call an element normal when it commutes with its adjoint. Examples of normal operators abound. Of course, if your C-star algebra is abelian, then all of its elements are normal. If you have an arbitrary C-star algebra and a so-called self-adjoint element, an element that's equal to its adjoint, then it is normal. If you have an element in a C-star algebra that's invertible and whose inverse is given by its adjoint, that is, if you have something called a unitary element, then again it is normal. You can use such elements to make new type of normal elements. For instance, if you start from a self-adjoint element and multiply it by the complex number I, then you have again a normal element. It's Q adjoint. Adjoint equals its opposite. Now, there are certainly elements that are not normal in general. For instance, a non-zero nilpotent matrix is automatically not going to be normal. So there are certainly operators that are normal and some that aren't. But what's special about normal element in a C-star algebra is that the C-star algebra they generate is automatically going to be abelian. So indeed, first remember that if you have a C-star algebra and you have a subset of that C-star algebra, you can look at the intersection of all the C-star subalgebras containing that subset, and you get again a C-star subalgebra. It's easy to check, which of course will contain that subset. So there is such a thing as the smallest C-star algebra containing a given subset, and this notion can be applied here to just a C-star algebra generated by, a normal element and the unit. But here I can give a much more explicit description of what that C-star algebra generated by these two elements look like. So let's fix A, some normal element in some unital C-star algebra. So let's think for a second. If you have a C-star algebra containing A, it must contain A star, and then it must contain every possible product of A with A star to various powers. So elements of the form A cubed times the adjoint of A to the power 7 times A to the power 6 times the adjoint of A to the power 9, and so on. Finite products like that. And in general, you don't know what to do with products of the form A star. But here, because A is normal, we can actually commute A and A star so that every such product is of the form A to some power times the A star to some power. Alright, so that's good, and we know that any linear combination of things like that together with the unit must be in your smallest C-star algebra generated by A and the unit. Okay, so that tells me that the set I've written here in the proof in curly brace must in fact be a subset of the C-star algebra generated by A and the unit. Pay attention, by the way, that in this curly brace, although it looks like I wrote an infinite sum here, I haven't, in the sense that really that my scalar coefficients T and M are assumed to be only non-zero for finitely many indices. So these are indeed linear combinations. All right, so we have a subset of our C-star algebra, and it's easy to check that this subset I've written, which I'm going to call, by abuse of language, the set of polynomials in A and A star, this subset must be in fact an algebra itself and a star algebra to boot. It's closed under the star operation. That's easy. You multiply things like that, add things like that, take the star of things like that. You still fall within this set. So the closure of this set is a C-star algebra, and it's inside the smallest C-star algebra containing A in the unit, but it itself contains A in the unit, so they must be equal. And so here you have a full description of the C-star algebra generated by A in the unit. And it's easy now to check that it is abelian. You simply have to check that this particular algebra of polynomials in A and A star is abelian, which is going to follow immediately from the fact that A and A star commute, because A is normal. And then the multiplication being continuous, the C-star algebra obtained by closing this set will again be abelian. So in order for me to state my theorem about the Galvan spectrum of the C-star algebra generated by a normal element without any ambiguity, I need a spectral invariance result. So let's say you're given a unital C-star algebra D, and you pick a C-star subalgebra E of D containing the unit of D. If you pick an element A of the C-star algebra E, then A is invertible in E, if and only if it is invertible in D. The consequence of that is that you can take an element A in the C-star algebra E, and you can consider it either as an element of E and calculate its spectrum in that particular C-star algebra, or you can look at A as an element of the larger C-star algebra D and calculate its spectrum there, and you will get, in fact, the same set. Now, this result in general, this theorem, is not true for arbitrary unital Banach algebras. It is, however, true for unital C-star algebras. However, what is always true is that the spectrum of A in the C-star algebra D is a subset of the spectrum of A in the C-star algebra E. And that's simply because if you are invertible in the smallest C-star algebra E, you're of course invertible in the larger C-star algebra D with the same inverse. So the story about C-star algebra starts now, and it's about the converse inclusion. So we begin with the observation that if you take an element of the C-star algebra E, or any C-star algebra here, doesn't matter, then this element is invertible if and only if its adjoint is. And that's a direct computation. You can simply check that the adjoint of the inverse of your element is the inverse of the adjoint of your element. That can be done by a straightforward computation using the anti-multiplicative property of the adjoint. Here I prove one of the two needed implication. A invertible implies A star invertible, but because star is involutive, of course, you get the other implication immediately. What do I do with this? Well, I'm going now to observe that this implies that the spectrum of an element and the spectrum of its adjoint are related in a very natural manner. Now again, here remember we're working inside an arbitrary C-star algebra, E or D, doesn't matter for this slide, and in particular not an abelian one, and I'm not assuming that my element A is normal at this point. So I cannot use the theory of characters or anything like that. I have to go back to first principles. So if I take lambda, an element of the spectrum of A, with respect to the C-star algebra E, well, that means that A minus lambda is not invertible, which in turn means that A minus the adjoint of A minus lambda cannot be invertible either, as we have observed. But I can calculate that as the adjoint of A minus the conjugate of lambda. So the conjugate of lambda must be an element of the spectrum of the adjoint of A, spectrum computed inside E. And you can do the same calculation exactly backward, or use the fact that the adjoint is an involution. From this, you conclude that the spectrum of the adjoint of an element is actually the conjugate of the spectrum of that element. So now I'm going to apply this observation to self-adjoint elements. More specifically, what I'm going to try to do now is prove my theorem for first the special case of self-adjoint elements in E. So let A be a self-adjoint element in E. First note that we have just shown that the spectrum of A computed in E must be a subset of the real line because it is equal to its conjugate. So now I wish to prove that the spectrum of A computed in E is a subset of the spectrum of A computed in D, since I already have the other inclusion. And the way I'm going to do that is I'm going to prove the reverse inclusion between their complements. So let lambda not be in the spectrum of A computed in D. First of all, note that if lambda is a complex number that's not a real number, then it cannot be in the spectrum of A computed in E, since that's a subset of the real number. So we have that done already. we're left with a case where lambda is in fact a real number. And then what I'm going to do is I'm going to define lambda sub n as lambda plus I over n for any n natural number. Note that because lambda is a real number, lambda sub n is a complex number that's not a real number. So what can I conclude from that? Well, I can conclude that a minus lambda n is invertible in E because lambda n is complex, not real, therefore it's not in the spectrum of A computed in E. So a minus lambda n is invertible in E, and of course a minus lambda is invertible in D. That's by the choice of lambda. Lambda is not in the spectrum of A computed in D. So you have a sequence of invertible elements in E that obviously converge to an invertible element in D because the limit as n goes to infinity of lambda n is of course lambda. The inverse function, of course, is continuous at a minus lambda, since a minus lambda is invertible in D. That's a general result about unidal Banach algebras. And so we can apply our continuity result to conclude that the limit as n goes to infinity of the inverse of a minus lambda n must indeed equal to the inverse of a minus lambda. But remember, a minus lambda n and a minus lambda inverse are both elements of the C-star algebra E. Okay? And the C-star algebra E is, in particular, closed. So the inverse of a minus lambda must actually be in E. And therefore, lambda cannot be an element of the spectrum of A computed in E. So, putting the implication backward, if lambda is in the spectrum of A computed in E, then it is in the spectrum of A computed in D. So now our theorem is proven in the special case of self-adjoint element of E, and I'd like to generalize it to arbitrary elements of E. So let A be an arbitrary element of E. Now suppose for a moment that A is actually invertible in D. Then I can conclude that A star A is also invertible in D, since A star is and the product of invertible elements is invertible. But on the other hand, do know that A star A is an element of E because E is a C-star algebra, so it contains both A and A star and the products. And it's a self-adjoint element, so applying what we've done in the previous slide, we conclude that the spectrum of A star A in E equals to the spectrum of A star A in D. And so I can conclude A star A is also invertible in E. All right? Now, the thing here is that the inverse of A star A in E, whatever it is, it's also the inverse of A star A in D, because inverses are unique, and I can calculate the inverse of A star A in D, because there, in D, I know I have something called A inverse, the inverse of A. I don't know if the inverse of A is in E, but I do know it exists in D. So you can do a calculation and check that the inverse of A star A is indeed given by the inverse of A times the inverse of the adjoint of A. Okay, so that product must actually be an element of E, even though each of its factor at the moment I have no idea if they are in E. So how do I actually prove that? Well, I do know that A inverse times the inverse of the adjoint of A is in E, and I also know that it's the inverse of A star A. So you can do a little calculation here, and you calculate that the inverse of A in D, must be equal to the inverse of A star A, which is given by this expression, multiplied by A star. You use associativity, and you see that's what you're left with. But if you look on the right-hand side, in fact, the inverse of A star A is an element of E. I've proven that thanks to the fact that A star A is self-adjoint, and therefore if it's invertible in D, if and only if it's invertible in E with the same inverse. And then you multiply that element of E with the adjoint of A, and that's also an element of E. So you have the product of two elements of E, that's an element of E. So A inverse is in E. And that's it, we're done. We've shown that if you have an element in E and it's invertible in D, then it must be invertible in E. But of course, if it's invertible in E, it's automatically invertible in D, that's obvious. And the preservation of, or invariance of spectra then follows from this very easily. So here's our little theorem, but it is quite useful, because now I can talk about the spectrum of an element in a C-star algebra with no reference to what C-star algebra am I using to calculate that spectrum. So if you take any element A in a C-star algebra with a unit, then it has a spectrum with respect to that big C-star algebra, but it also has a spectrum with respect to the C-star subalgebra it generates together with the unit and whoever else you want in between. But the spectrum of that element is always the same. So we can now state our main result about the computation of the Galvan spectrum of a C-star algebra generated by a normal element without any ambiguity. So we fix some unital C-star algebra, and we pick a normal element in that C-star algebra, which we call A. The C-star algebra generated by A in the unit is abelian, so we can look at its Gelfand spectrum, which is the set of all its characters. And what our theorem asserts is that there is a map which to any character omega of the C-star algebra generated by A in the unit, we can associate the value omega of A, which will be in the spectrum of A, and that this map is in fact a homeomorphism. We call this map A hat because it is indeed the Gelfand transform of the element A, seen as an element only on this abelian C-star algebra, the C-star algebra generated by A and the unit. In general, the C-star algebra Gothic A in the statement of the theorem here is not assumed to be abelian. It doesn't have necessarily any character. Its Galvan spectrum may well be empty. So this is not the Gelfand spectrum we're talking about here, or the Gelfand transform is not related to that Gothic A unital C-star algebra. All of those Gelfand spectrum and Gelfand transforms are discussed within the context of the unital abelian C-star algebra generated by A and the unit. So we already actually gathered quite a bit of information about the Gelfand transform in our previous lecture. For instance, we already know that the Gelfand transform of A is indeed surjective, that is the range of the Gelfand transform of A, which is the same thing as the spectrum of the Gelfand transform of A, is indeed equal to the spectrum of A. We also do know that the Gelfand transform of A is a continuous function. It's a continuous function from the Gelfand spectrum to C, to the complex numbers. So what's left to prove here is that the Gelfand transform of A, which we now know is continuous and surjective, is also injective. So let's prove that by taking two characters of the C-star algebra generated by A in the unit, which happen to agree at A. Let's call these two characters omega and eta. So omega of A equals eta of A. Since they're characters, they're star morphisms, so in particular omega of A star is indeed the conjugate of omega of A, which by assumption is the conjugate of eta of A, which again, using the star morphism property, is eta of the adjoint of A. And then, because both eta and omega are multiplicative, they are, after all, again, star morphisms, we conclude that on any product of the form A to the n, A star to the power m, they must agree as well. And therefore, any linear combination of those various products will have the same image by both omega and eta, since omega and eta are linear. And now the set of these expressions, this linear combination of those products, is in fact dense in the C-star algebra generated by A in the unit by the Stone-Weierstrass theorem. And so we conclude that since characters are in particular continuous, and since they agree on a dense subset of the C-star algebra generated by A in the unit, they actually agree on the whole C-star algebra of A and the unit, which means that indeed we have shown they're the same character for the C-star algebra, and the Gelfand transform of A is injective. Since it was already surjective, it's bijective. So we now have a continuous bijection, which is not usually enough to conclude it's a homeomorphism, but here it's a little bit different because, of course, the Gelfand spectrum of the C-star algebra generated by A in the unit is a compact space. So actually, being a continuous bijection does imply that the Gelfand transform of A is a homeomorphism as claimed. Using this observation, we are now going to construct the continuous functional calculus for normal elements of C-star algebras. In opera theory, when we talk about functional calculus, we typically mean that we want to apply a function that's reasonably regular to certain kind of operators or elements of certain Banach algebras. The most general such construction is the so-called holomorphic functional calculus, where if you give me some unital Banach algebra and you pick an element A in that Banach algebra, and then you take a function f that's holomorphic on some open set containing the spectrum of A, then we can define the element f of A using an extension to opera theory of the Cauchy formula. What we can then try to do is extend the classes of functions we could use beyond, say, holomorphic functions with, for cost, reducing the type of elements we can hope to apply the functional calculus to. This is what we're going to do here. We're going to be able to apply continuous functions to normal elements of C-star algebras. So let's try to discuss this a little bit. Let A be some normal element in a unital C-star algebra. If we take a function f that's complex valued and continuous over the Gelfand spectrum of the C-star algebra generated by A in the unit, then we can define a new function called phi of f here by composing f with the inverse of the Gelfand transform of A, which we just saw is a homeomorphism, and that will be a complex valued continuous function on the actual spectrum of A. And of course we know that this phi thus defined is a star isomorphism from the continuous function on the Gelfand spectrum of the C-star algebra generated by A in the unit onto the continuous function on the spectrum of A. We can even calculate its inverse, as is done here. It simply maps a function in the continuous functions over the spectrum of A to that function composed with a Gelfand transform. So what is the idea of the continuous functional calculus? Well, here it is. For, again, A being normal in some unital C-star algebra, if you pick a function f that's complex valued and continuous over the spectrum of A, then the unique element in the C-star algebra generated by A in the unit, whose Gelfand transform is going to be f composed with this Gelfand transform of A, is denoted by f of A. With the notation in my little preamble here, it means simply that you take this function f, apply phi inverse to that f, and you have an element of the continuous function on the Gelfand spectrum of C star of A in 1, and whatever that element is, it must be the image of an element in the original C star algebra. You call that f of A. So let's be even more formal. What we're doing here is we are defining a new star isomorphism, which goes from the complex valued continuous function on the spectrum of A to the C-star algebra generated by A in the unit. And the star isomorphism is defined by composing two already known star isomorphisms. We're composing the inverse of the Gelfand transform with this phi inverse in the preamble. So, because it's a composition of two star isomorphism, it is itself a star isomorphism, and that's what we call the functional calculus. So not only do we have the ability to calculate element of the form f of A for f continuous on the spectrum of A, but we actually know that this assignment is in fact having all the nice properties of being an algebra morphism and preserving the adjoint. So for instance, as an example, f times g applied at A is f of A times g of A. So same with the adjoint, the conjugate of A applied to A is f of A adjoint, and then we also know that of course this is a linear map. So that's what's called the continuous functional calculus. There are many important applications of the functional calculus. It's a very basic tool of C-star algebra theory. So let's start with some simple observation. Again, we have a unital C-star algebra. We pick a normal element in that unital C-star algebra, and you pick your favorite complex valued continuous function over the spectrum of A. Then you could ask yourself, what's the spectrum of f of A, this element we just defined, and it's simply f of the spectrum of A, the image by f of the spectrum of A. And the calculation relies simply on the Gelfand transform properties. It's a very, very straightforward calculation. So basically the spectrum of f of A is the spectrum of its Gelfand transform. And then if you look at how we define our functional calculus, it will be immediate that it is therefore the image of the spectrum by f. That's a very simple calculation, but it is of course a very welcome property. So for instance, if A is normal, and you apply to A a function which is valued only in the real numbers, then you could prove as a little exercise that then f of A is self-adjoint. That's the sort of consequences that we can immediately extract from this so-called spectral mapping theorem. Another series of important consequences follow from the interrelation between the functional calculus that we just defined, the continuous functional calculus, and star morphisms, in particular unital star morphisms. So my first observation is that in some sense there is a commutation relation between the continuous functional calculus and star morphisms. So you fix two unital C-star algebras and some unital star morphisms between them. And if you pick a normal element in the domain of phi, then the first observation is that the spectrum of phi of A is a subset of the spectrum of A. That's useful observation because if we want to talk about functional calculus, we need to work with continuous functions on the spectra of those elements, so this relation will prove helpful. And with this observation in mind, if f is continuous on the spectrum of A and complex valued, then you apply your unital star morphism to f of A, gives you the same answer as having applied f to the result of applying your star morphism to A. So as you see, the functional calculus and the star morphism sort of commute in some sense here, and this makes sense because of the inclusion between spectra. So if you take a continuous function over the spectrum of A, you can restrict it to a continuous function over the spectrum of phi of A. So everything I've written here is actually meaningful. So let's prove this result. So let's prove first the inclusion of spectra, and I'm going, as often is the case, to prove actually the reverse inclusion between the resolvent set that is a complement of the spectra. So indeed, if we assume that for scalar, some scalar lambda, A minus lambda is invertible in your C-star algebra A, then because the map phi here is a unital star morphism, we can calculate very easily that phi of A minus lambda times phi of the inverse of A minus lambda is phi of the product of A minus lambda with its inverse, which is phi of the unit of the domain of phi, which is the unit of the codomain of phi. And that calculation carries just as easily when you multiply those two factors the other way. So we get that phi of A minus lambda, which by linearity you can take the lambda out, is also invertible in the codomain of phi. So if you start from some lambda that is not in the spectrum of A, then it's not in the spectrum of phi of A either. So once we take the complement, we conclude that the spectrum of phi of A is indeed a subset of the spectrum of A. So let's now turn to the relation between our unital star morphism phi and the continuous functional calculus for the normal element A. So let's introduce again this collection P of these functions, which informally you could call sort of polynomials in the variable and its conjugate. And this is interesting to us because this is a unital algebra closed under conjugation within the C-star algebra of complex valued continuous functions on the spectrum of A. That's by construction. It's easy to check. It's indeed closed under multiplication. It's a linear space, obviously closed under scalar multiplication, and it contains the constant function equals to 1 on the spectrum of A. It also contains the identity, and as such, it separates the point of the spectrum of A. So now the spectrum of A, of course, as you well know, is a compact subset of the complex number, so we can apply the Stone-Weierstrass theorem to conclude that this set P is dense in the C-star algebra of complex valued continuous function over the spectrum of A. And using the fact that the functional calculus is a star isomorphism, and therefore it's in particular continuous, and observing that if you take a function f that is complex valued and continuous over the spectrum of A, then f must be a uniform limit over the spectrum of A of some sequence of elements in that P set, we just showed that, then we can conclude that you could calculate f of A as a limit as n goes to infinity of a sequence of simply these elements of the set P applied to A. Okay? So why this is useful is because you see that the set P is sort of an algebraic object. If you take an element of P and you apply it to A, what you get is a linear combinations of powers of A times powers of its adjoint. And so as such, of course, these are notions that play well with morphisms. So indeed, as phi is a unital star morphism, if Pn is some sequence in my set P that uniformly converges to the function f I chose, then we have that for every natural number n, phi of Pn of A equals Pn of phi of A. That just owes to the fact that phi is a star morphism, preserving the unit, and Pn's are, as I said, some sort of linear combinations of products of powers of A and powers of its adjoint. But therefore, by continuity, as star morphisms are continuous, phi of f of A is the limit as n goes to infinity of Pn applied to phi of A. So now the question is, what is this limit on the right-hand side? And again, I'm going to use continuity of the functional calculus. Since Pn converges uniformly to that function f on the spectrum of phi of A, simply because that's a subset of the spectrum of A, and that's how I chose my Pn to begin with, I can apply continuity of the functional calculus to conclude indeed that the limit as n goes to infinity of Pn of phi of A is simply f of phi of A, and so we have shown the equalities that we want. That's a very useful result. And we're going to conclude this lecture with an application of this useful result. So we've learned that star isomorphisms between unital C-star algebras are always isometries. That's an important result, and we already used it several times when talking about the Gelfand transform in particular. However, what about injective star morphisms? It would be tempted to think they're also isometries in a naive sense, because what you could do is, well, restrict their codomain to whatever the range happens to be, and it looks like a star isomorphism, except we have one little glitch in this reasoning, is that we don't know a priori that the range of an injective star morphism is a C-star algebra. Certainly it is a star algebra, but is it closed? And it turns out that the answer is positive. It turns out that indeed injective star morphisms are also isometries, but it is not obtained through the same reasoning as we did for star isomorphism, or not quite exactly. We are going to invoke the functional calculus for this proof. So let's fix two unital C-star algebras, and let's pick phi, injective unital star morphism between those two C-star algebras. And the conclusion is, well, phi is an isometry, and as a consequence, the image of phi is a unital C-star subalgebra of the codomain of phi. So let's now prove our theorem. What we borrow from the proof that star isomorphisms are isometries is the idea that an injective unital star morphism is going to preserve the spectrum of Selfadjoint elements. So let A be a Selfadjoint element in our C-star algebra. We know, since phi is a unital star morphism, that the spectrum of phi of A is a subset of the spectrum of A. Let's assume that they are in fact distinct, and that lambda be a number in the spectrum of A but not in the spectrum of phi of A. Since the spectrum of A is a compact Hausdorff space, it has very strong separation properties. If we take two disjoint closed subsets of the spectrum of A, there exists a real-valued continuous function on the spectrum of A which takes the value 1 on one of those closed subsets and 0 on the other. So in particular, there exists a function f, real-valued, continuous on the spectrum of A, which takes the value 1 at lambda, yet is 0 on the entire spectrum of phi of A. So what do we know? We know that since phi is a unital star morphism, phi of f of A equals to f of phi of A. Second of all, since f is real-valued, and since A and therefore phi of A is a Selfadjoint element, so a normal element, f of phi of A is again a Selfadjoint element in the codomain of phi. We also know by the spectral mapping theorem that the spectrum of f of phi of A is equal to the image of the spectrum of phi of A by the function f. And by our choice of the function f, this is a singleton 0. So f of phi of A is a Selfadjoint element with spectrum 0, and so it must be the 0 element. Now on the other hand, as I just said, f of phi of A is equal to phi of phi of A, phi of f of A. So phi of f of A is also 0. Okay, so f of A is in the kernel of phi. That would normally force f of A to be null, since phi is injective. However, we know that f of A is not 0. Why do we know that? Because by the spectral mapping theorem, I know that 1, which is f of lambda, is in f of the image by f of the spectrum of A, and therefore 1 is in fact in the spectrum of f of A. So f of A is not the 0 operator, and that's a contradiction. So we must have that the spectrum of A equals to the spectrum of phi of A. Now the rest of the argument is familiar. If we take an element, a Selfadjoint element in our C-star algebra, and we know that phi of A and A, for that Selfadjoint element A, have the same spectrum, they have the same spectral radius by definition, but the spectral radius of a Selfadjoint element is its norm, and since phi is a star morphism, phi of A is also a Selfadjoint element. So we get that the norm of A equals to the spectral radius of A equals to the spectral radius of phi of A equals to the norm of phi of A. So phi is certainly an isometry on the Selfadjoint element, but it's a star morphism, so it's going to be an isometry on all of A, because if you take an arbitrary element A, then the square of the norm of A, as usual, is, by the C-star identity, the norm of A star A, using the isometry property on the self-adjoint elements, that's also the norm of phi of A star A, but phi is a star morphism, so that is the norm of phi A, the adjoint of phi of A times phi of A. And again, using a C-star identity in the codomain of phi, that's the square of the norm of phi of A. So we've shown that phi is indeed isometric. So this is very interesting. Injective star morphisms are automatically isometric, just as were, of course, star isomorphisms. Now, to conclude, the range of phi, that is the image of the C-star algebra domain C-star algebra by phi, is the image by an isometry of a complete space, because C-star algebras are complete, among other things. Therefore, its image is also complete. And now, what is the image by any star morphism, injective or not, of a C-star algebra? Well, for sure, it's a star algebra, because it's easy to check. This is just the algebraic properties that follow. And so we have a closed star algebra inside of a C-star algebra. And so the range of my map phi here, my injective unital star morphism, is itself a C-star algebra. It has a unit because the star morphism is unital. So this leaves us with one interesting question, which we will address later. If you give me an arbitrary unital star morphism, but it's not necessarily injective, is it going to be an isometry, and is its range going to be a C-star algebra? And the answer is no. In general, unital star morphisms are certainly not isometries, because they can have a kernel that is non-trivial. However, their range will always be a C-star algebra. And the reason for that will owe to the theory of ideals and quotient of C-star algebras, as we will discuss in a future lecture.